Welcome back. It took me a while to start making videos again due to some academic engagements. In this video, we will see that how we can generate box plots of docking scores in different proteins. So this is a structure of protein and can be used for docking of ligands to fulfill the purpose of virtual screening, binding affinity analysis, or structure-based drug designing, etc. The PDB ID of this protein is 1 ATP and is a kinase. Active site analysis was performed and then dock compounds into the active site. If we look closely, then the conformation of the ligands and its protein-ligand interaction can be used to produce binding affinities of the ligands. So in this pose, two ligands are docked and three different conformations produce three different binding affinities against the same protein. For example, compound 1 gives the values of -1 to -3 and another compound 2 gives us the value of -8 to -10. Please remember that smaller value is best. Generally, we will take value of -10 out of these values and we will say that compound 2 is doing good in the active site and can be considered. However, for showcasing the results, we may generate the box plots for these values. Along with the showcasing, there are several technical reasons due to which we need to generate the box plots for these values. These box plots can be combined like this and can visually appeal the reviewer. Now suppose that the same compounds were also docked into the active site of another protein. Let's call it protein 2, and here you can see its box plots. How these are different from each other, we will discuss them technically in some other video. In this regard, it is important to know that we want to generate the box plots from the files in which all of the values of the compounds have been saved. So here's the summary of logical steps which are then translated back into the code ahead in the rest of the video. So what will we do? We will call the packages and install them if required. Tell R about our folder in which all files are stored. Set the working folder of R to the above path. Make a list of file names with complete path. Read the files and store the rows and columns using lapply function. After it, we will make a data frame by cleaning, reading and combining all of the rows of the files. We will make box plots of all the docking scores of the ligands against all proteins. Change the box plot to phasic grid type and alter some of the plotting values and generate second version of the box plot. So these are some of the CSV files produced after the docking of nearly 8 ligands or compounds into 8 different proteins. This data is provided after proper docking by my very competent student, Ms. Samavia. Thank you, Samavia. Each file represents the docking scores of the 8 ligands for each protein. Let's open one of the file and see the structure of the file. Here you can see two different columns and several rows. First column represents the name of the ligand and second column represents the binding affinity. In the first column, you can see that the name of the ligand has unnecessary information which will be cleaned later on by using the regex or regular expression. Here, if we scroll down after sorting, then we can see different rows for different compounds. So let's close the Excel. Same is true for all of these files. Let's see the code that I have prepared for this video. This environment is provided by RStudio. You need to install R software first and then you will need to install RStudio for getting up to here. This code is available at my GitHub repo. The link is given below in the description. In the first two lines, we are actually installing two packages which are tidyverse and ggplot. As I have already installed it, so I do not need to run these two lines of code. In the following two lines, we are calling the packages. At line 7, we are storing the path in the object of main folder. Please remember that we will use // instead of backslashes. setwd function is setting the working folder in R. Later all the files will be read and written back to the same folder. At line 12, function of list.files produce a character vector of the names of files currently stored in the main folder. Here, recursive is true to recurse into the directories. Pattern is an optional regular expression and will return file names which match the regular expression. We have .csv as a regular expression so that it can match or can get all of the files which are CSV from the folder. Full.names is prepending the directory part to the file name. Let's see the data object. Here you can see the full paths of all files. Now let's see the type of the object data. It is a character vector. Now we will read all of the rows and columns of all files by using the function of lapply. In brackets, we are giving the complete paths as data and reading the CSV by using the read.csv function. It combines both arguments and present as a list. Let's see the data files object and its class. Before going into the description of this, so you can see here this convention. For this, we are using the package of tidyverse. After completion, the final output will be stored into df2 object. In this line, we are binding the rows of all files currently stored as listed in data files. Reduce function combines the first two elements, then combines the result of that call with the third element, and so on. In the second line, we are making another column in the data frame with name protein ID. In this column, we are going to store the substring of ligand column. This substring will be the first 5 characters, which represents prot A. In next line, we are changing the lower characters to upper characters for the column protein ID. In this line, we are cleaning the column of ligand and removing everything from start until seconds underscore using gsub function with regular expression dot star underscore. Double quotes here without anything in between represents that after matching the part, substitute it with nothing. Here you can see that how much regular expressions are useful. Suppose we are giving the same text from the ligand column into this text box, and we will write the regular expression over here in this text box. The regular expression is dot star underscore. As we write the regular expression, it is searching for the same thing in the text which we have provided in the text box, and it is considering the highlighted characters. Finally, we have df2 object filled with our data. In these lines of code, we are going to use ggplot function, which requires data frame means df2 object, in our case x and y axis values, and we want to color or fill the components of the graphs. We are using values in protein ID column for differentiating according to different proteins. Plus sign represents that some more properties of ggplot are also here. geom_boxplot function is a function to produce box plots. These are some of the arguments for formatting and labeling graph. We will do another video on these arguments. Let's run it and see the plot. Nice. Now make facets by using facets_grid function as in this line of code. Great. It is time to save the graph as PDF with defined width and height. You can also save the graph in PNG format by changing the extension of PDF to PNG. Now generate the second version by changing the above command from protein to ligand. Let's see this one. Save it as well for your supervisor to decide. The difference in these two versions is that in this graph, we are combining the results of ligands according to each protein, whereas in this graph, we are combining the results according to each ligand. Now the choice is yours, so that's it for now, and we will meet in the next video. Peace. After completion of the final output will be stored into df2. What's happening? 2. After completion of the final output. So what was that? After completion, the final After completion, the final output will be stored into DFT. What is this DFT? After completion, the final output will be stored into now it's good, df2 object. Yes.